Start. Independent events, X9G. There is only one thing that you guys need to know when they ask about independent events, and usually they have to tell you it's independent. So here's a couple of things you need to remember. Remember, for conditional probability, the chances of the current event is dependent on a previous event. That's literally what conditional probability is. So when you think of conditional probability, the chance of something happening now depends on what had happened before. The example I like to give you logically is if I said the probability of tomorrow raining, so tomorrow is Thursday. So what's the chances of tomorrow, which is Thursday, raining, given that today rained? You see, usually logically, if today rains, you might think that tomorrow either is less likely to rain because you already had rain, or you might think it's more likely to rain since we're hitting winter. Therefore, if today rains, tomorrow might have a better chance of raining, right? But regardless, you wouldn't say it is equal every day. That's a 50-50. You would say that whatever has happened today, which is Wednesday, likely has an effect on Thursday. It's like gambling when people bet on, they see that, you can do a gambling where you bet if it's large or small. And if they see it's large, then they might think, well, the next one can't be a large. They think it's small, right? But what they're doing is they're thinking that the probability of the next event happening has something to do with what happened before. So they think because it's large, 5 times in a row, they think the chances of it being large again cannot be. It has to be less likely. But the reality is that the probability is consistent. When it's consistent, that means it's independent. Okay, like flipping a coin. Every time you flip a coin, the chances of getting heads and tails doesn't change. It's always 50%. That's independent. Dependent means that there will be a change. That whatever happens, what you did beforehand will affect on what will happen later. Okay, so that's the difference between the two. So conditional is actually the opposite of independent. In other ways, they could have called it dependent probability, and then they could have called that independent, and it helps you understand the difference between the two. So today's lesson, this is your conditional probability rule. Okay, so things that we tried to talk about in 9F. So just to remind you again, if you draw a tree diagram, let's say I flip a coin. Actually, I'll do the raining scenario so you can understand. Chance of today raining, we don't know yet. Let's call it, I'll just make it up. Let's say it's 70%, so 0.7. You got 70% chance of it raining today, and you have 30% chance of it not raining today. So that's today. Say tomorrow, so now you got two extra scenarios. If today did rain, tomorrow might rain again. And then it might not rain, right? Let's say, and this is where if I use a conditional probability, if I said whatever happens tomorrow is dependent on what happened today, I could say something like this. If today rained, then tomorrow is less likely to rain. Then I could have 40% chance of it raining because today rained. That means these two are dependent. Tomorrow's raining has an effect based on what happened today. So that means if it's 40% chance, if yesterday rained, that means this is now 60% chance of not raining. But let's say it was the other scenario. Let's say today didn't rain. If today didn't rain, which is 30%, then tomorrow has a more higher chance of it raining. So I could say something like, you now have 0.8. Because today didn't rain, the weather's brewing up, tomorrow's more likely to rain. So here in this scenario, be rain and then 0.2. So 20% chance it doesn't rain. But this scenario that I'm coming up with at the moment, this is a conditional probability. This has dependence. The tomorrow's probability has a dependence on what happens before. Where does this rule come from? Literally your multiplication rule. We're saying PR of R, so if I wanted to know what's the chances of today raining and tomorrow not raining, how would you do that? What you would have done is you would have said, well, the chance of today raining is here. That's 70% chance. And then the chance of tomorrow not raining is 60% chance. So what you're really doing is you're doing 60% of the 70% chance of raining. So what you're doing here is you would then say it's 0.7 times 0.6. But what does the 0.7 and 0.6 represent? 0.7 represents the chances of it raining today, so on a Wednesday. That's 70% chance raining today. Tomorrow, if it doesn't rain, that's 60% chance that it won't rain tomorrow. But that's dependent on the fact that it rained today. That's the condition. So this is not just probability of not raining. This is the probability of not raining given that it rained the day before. See that little vertical line and that R component? That's describing what happened before. That's what this formula is saying. This formula is saying if you wanted to go from rain, not rain, it's actually the first event times by the second event given that the first event had happened. That's why it's conditional. So what's the difference in 9G and 9F? Well, if it's not conditional, then we're saying that in an independent scenario means that, well, what if tomorrow doesn't have an effect? Or today doesn't have an effect on tomorrow? Tomorrow's chances are always going to be the same, like flipping a coin. Then if we're saying that, the formula changes by one small detail. Right here. That means the chances of not raining doesn't matter what happens the day before. It's just the chance of raining or not raining. So that's why the formula here, you can see there's only one small detail that they change. It is the probability of B given A. Instead of it's actually depending on what happened before, the rule changes to it's just a probability of B. So I'll say that again just so that you understand what I'm trying to say. I'm saying for it to be independent, if today rained was 0.7, 70% chance, that means there's 30% chance it doesn't rain. If it's independent, it means that tomorrow it's still 70% chance because it has no dependency on it. And that means the chance of not raining is 0.3. That means this one is R and not R. These two, this is what independence looks like. Because whatever happens the day before does not affect the chances of it occurring. So what we have here instead now is PR of rain and not raining is equivalent to chances of it raining, which we knew was 0.7, times with the chances of, now it's not R dash given R, it's just actually the chances of R dash. That's why we say it's just R dash. And that's 0.3. Can you see the difference between the two? So on one scenario, this one was a scenario where I was making it's conditional. All these probabilities depend on the one before. Whereas this one, the probabilities of the next day does not depend on what happens before. So the only small change in the formula is that PR of R dash is just PR of R dash. It has nothing to do with given A. So this is what the small definition changes, and this is your rule that you test. This is conditional. So PR of A and B is A times B, but it depends on A. Independent events, 9G, so this is 9F. This is 9G. 9G is saying, well, if B doesn't actually depend on A, then you're really just finding probability of B. This literally, if you didn't understand the theory and I just simply said, this is all you have to memorize. That's 9F, that's 9G. And in exercise 9G, if they tell you it's independent, this is the one you use, not that one. Okay, and how do you prove it's independent? If this works out to be true. If you found the intersection of whatever the situation was, and then you multiplied just the probability A and probability B, and they're both equal, it's independent. If you multiply these two probabilities, but it doesn't actually equal the actual intersection, then they're not independent, therefore it must be conditional. Okay, so I'll do an example so you can see how you test it. So 9G, you just need to know one rule. But the theory that I'm teaching you actually started off with understanding what conditional is. And that's the harder one. 9F is the one you want to practice. Okay? Let's do an example. Here we go. So this is how we change a conditional probability to independent. Independent rule. All right, let's do an example. I'm going to ignore that simple example there. Let's go to this one. Here we go. This is what they'll do. They'll give you a set of numbers. So here I've got an experiment that consists of drawing a number at random. These are numbers that you can pull out. 1, 2, 3, 4, 5, 6, 7, 8. So you've got 8 numbers that you can pick. Let's say the event A is the numbers 1, 2, 3, and 4. Okay, so chance of getting A is any numbers that's 1, 2, 3, and 4. Group B is any numbers that is 1, 3, 5, and 7. And then group C is the numbers 4, 6, and 8. Okay? Now, if I want to know if they're independent or dependent, it's just the simple rule. But we're going to start off by finding the probability. What's the probability of getting A? If I know there's 8 numbers there, 1, 2, 3, 4, 5, 6, 7, 8, what's the chances of getting A? What's the chance of getting A? So A is 1, 2, 3, and 4, and you've got a list of 8 numbers. My year 8s can do this one. Yeah. There's 4 out of 8 options there. It's 1/2. This is what we practice. This is 9A to 9E that I was saying. It's year 7 to year 10 mathematics. 8 numbers. There's 4 in group A, so 4 out of 8. So it's half. What's the chance of getting B then? Same. 4 out of 8 again. 4 out of 8. Half. Very good. What's the chance of getting C? 3 out of 8. My year 8s would be laughing at the moment. The only thing they don't know is what independent actually means, right? So here, if we want to test if is A and B independent, according to the rule I just gave to you, if they are independent, then this rule should work. Probability of A intersection B should equal to probability of A times probability of B. So let's test that. Probability of A times probability of B. What does that equal to? So I actually had probability of A is half. Probability of B was also half. So if I multiply them, I get 1/4. Very good. So I get a quarter. Now, we need to find, does probability of A intersection B actually equal to 1/4? We're testing it. How do you find probability of A intersection B? Well, first you need to find A intersection B. Are there any numbers that is in common in group A and group B? What's common in group A and group B? 1 and 3. So I've got 1, 3. This one has 1 and a 3. So that means group A intersection B must be 1 and 3. But what's the chances then? What's the chances, knowing that there's 2 numbers, 1 and 3, what's the chances of me picking 1 and 3 if there are 8 numbers in total? 2. That happens to also simplify to 2 out of 8 is 1/4. That means it must be independent. So here you can then say, since PR of A intersection B is equal to probability of A times probability of B, which is 1/4, therefore it is independent. These are independent events. And to remind you what independent events means that every time you flip a coin or you randomly choose B or you randomly choose A, it doesn't matter if you got A beforehand or you got B beforehand, B will always have the same probability and A will always have the same probability. It doesn't get affected by what happens before. Kind of like the gambling example I was saying. Doesn't matter how many times that you flip a coin that becomes tails, the chances are still 50%. Doesn't change. Let's try the next one. Is A and C independent? So we do the same thing. If we want to know if A and C is independent, then you test probability of A times probability of C. A was 1/2, C was 3/8. So you multiply them together, you get 3 out of 16. Now to prove it's independent or not, you test it. What's the probability of A intersection C? To work that out, well, but you need to figure out, is there any commonalities between A and C? Is there anything in common with A and C? So A intersection C. Any numbers? They've got a 4, so I can see there's a 4 here. This one has a 4, and that's about it. A and C has a 4. That means, if I ask you what's the chance of getting A intersection C, well, there's only one number out of the 8 numbers. Your chances are 1 out of 8. Are these independent? No. That means when you're getting C, the chance of getting C does matter if you got A first. It does have an effect on it. And we don't know the scenario. We haven't actually been described what the scenario is, but we do know it's not independent. So it's just based on one formula. If it fits, if it works out, it is independent. Okay? But if it's not, maybe conditional, it might not be conditional. It might just be irrelevant. Right? So here we can say probability of A intersection C does not equal to probability of A times probability of C. Therefore, not independent. So that's why 9G is easy. 9G, you're just testing if it's independent or not. That's all they want you to know, because the calculations actually only occur after you know if it's independent or whether it's conditional, because it just changes the multiplication rule. Okay, so when you move through the tree diagram branches, when you multiply them, it just matters whether the probabilities change or they don't change each time.
Can you illustrate the independent rule on the Venn diagram?
Yeah. A typical one is your heads and tails. So heads and tails are rolling a dice. Those are the typical independent events that's why students generally don't realize why the probabilities are consistent. But if you try it, chance of getting H is half. Chance of getting tails is also half. If I did it a second time, if I flipped it the second time, you still get H, tails, H, tails. So half, 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 right? But we're questioning, is it always going to be half, or does this actually depend on what happens before? So you can test it by saying probability of H times probability of, I guess I'll do tails just so that we can see different letters there. Probability of H times probability of T works out to be a quarter times a quarter. Okay? That gives you 1 on 16. Oh, sorry, what am I doing? Half times a half is a quarter. Right? But then if I asked you, what's the probability of H intersection T? Well, let's work it out. You could get HH as your sample space, HT, TH, or TT. What's the chances getting H on the first go, T on the second go? Yeah. There's only one option out of the 4 options. So in this case, probability of H intersection T is actually equal to probability of H times probability of T, hence independent events. This is why when you draw the third diagram and you draw the fourth diagram, independents imply that the probabilities never change and it doesn't depend on it. That's why if you got 5 tails in a row, it doesn't mean the next one has to be heads. It's not like God's playing with you. It's actually just probability. That it just happens to be 50%, 50%, 50%. The chances do not change. It's just based on random luck. Yeah? So that's what independent events mean. So, and that's more relevant for application questions when you're doing things like, you know those questions where you got a basket and let's say you've got seven blue balls or marbles and then 8 green. So you might have a chance like, what's the chances of getting blue and then green? You would say out of 15, there's 7 blues, 8 greens. And then if I said, if you had to replace, do you remember the word replacement? So if I do replacement, so if I took the ball out, I took a blue for the first time, then there should be 14 balls left. But if I replace it, it becomes 15. So that means there's still 7 out of 15 for blue. Now, why is this special? This is what we call independent events because it doesn't matter what you get before. It doesn't affect the probability of the next one because you're replacing it. Everything's always the same. But if I didn't say replacement, so no replacement, there'll be one less blue in this scenario. This now depends on what you got in the first go. If you got a blue in the first go, it affects the chances of the next one. This is conditional. Okay, so that's why you got to know the difference between independent and conditional because it's whether it's repetitive or it's not. And at a year 12 level, we do things where we assume if everything was consistent and it's always going to be the same, you can actually do calculations that go on infinitely, which is what the study of year 12 probability is about. That's why you need to know 9F, 9G. Okay? Now, let's pick a question to get you practicing 9F, 9G. I'll leave those two examples for you to try there. But let's go to, in your OneNote, I've already inserted the year 12 textbook question. If you go to 9F, I've chucked in 9F, I've chucked in the year 12 textbook over here. So 13B covers conditional probability and independent events. It's both 9G and 9F combined. Yeah? Let's pick a question to do. Let's do the first one. First one's nice because it's to do with raining. Let's try this one. So you can see how it works. Here we go. Using a tree diagram is probably the first hint to solve this problem. So let's read the question. It says, in a certain town, the probability that it rains on any Saturday, so rains on any Saturday, you got 25% chance. So the first thing I'm thinking about is, on a Saturday, for it to rain, you got 0.25, 25% chance. What's the chance of it not raining then? 75. Yeah, very good, 0.75. So 75% chance of it not raining. That's on a Saturday. So this is for Saturday. Then they say if it rains on Saturday, so if it rains on Saturday, then the probability of rain on Sunday is now 80%. So they're saying if it rains, and this is now Sunday, for it to rain on Sunday, there's an 80% chance only if it rained on Saturday. So hence it's conditional probability there. Okay? So we can see, therefore, what's the chance of it not raining on Sunday if it rained on Saturday? 20%. Very good, because this was 80%. So there must be a 20% chance of it not raining on Sunday if Saturday did rain, based on that condition. Okay, so this is the condition they gave you. But it had to be if it rains on Saturday, then the chance on Sunday is 80%. Then they gave you another one that says if it does not rain on Saturday, so if it doesn't rain on Saturday, the probability of rain on Sunday is now 0.1. So what changes here? Raining on Sunday, if it didn't rain the day before, is now 0.1. This is now not rain. That must mean, what's the chance of it not raining on a Sunday if Saturday didn't rain? Very good, 90%. 0.9. Now we can start answering the question. So they're saying, for a given week, so in a 7-day period, find the probability that it rains on both Saturday and Sunday. So essentially they're saying, what's the probability of raining on Saturday and raining on Sunday? This question is a conditional probability because this raining is not just probability of R on Sunday, it's dependent on rain on Saturday. So technically, chances of raining on Saturday is probability of R multiplied to, now this second R is not just second R, it's the probability of raining on Sunday given that it rained on Saturday. So those two R's are different. This is a Sunday given that it rained on Saturday. That's what it's really saying there. That's conditional probability rule. Put them together, that's 0.25 times 0.75. Or other ways, you can think of it as a quarter times 3/4. You got 3 out of 16 chance that it'll rain on Saturday and rains on Sunday given that Saturday had rained. Okay? Oh, it's 0.8. Whoops. I looked at the wrong number. 0.8 is 8 out of 10, which is what, 4 out of 5? 4 out of 20, my bad. So 4 out of 20, then it becomes 1/5. There we go, these 4's cancel out. My bad. And then B, so that was part A. Part B, it rains on neither day. In this case, neither day would be 0.75 times 0.9. So neither day, B is neither days. Probability of not raining on Saturday and not raining on Sunday is equal to probability of not raining on Saturday times probability of not raining on Sunday, given that it didn't rain on Saturday. So this is Sunday, this is Saturday. It's that conditional part that you need to understand. Okay, so the notation is key because you have to be able to read the notation to understand. Sometimes they give you the notation and you have to figure out the tree diagram. If you got the tree diagram, it's easier to answer the questions. So this one would then be 0.75 times by 0.9. That's like saying 3/4 times 9 out of 10. And there's nothing I can simplify there, so it's 27 out of 40. What about the last one? So this one usually gets students for the first time when they're not yet used to finding probability. They're asking, what's the probability of raining on Sunday? What do you think the most likely answer that students normally write for part C? 80%. Most students will write that because they think that branch means rains on Sunday. That's not what it is, because this is also raining on Sunday as well. See? This is also raining. Why is it that one? A lot of students will write 80%. The difference is to understand this is not R, this is R given that R had occurred. This is raining on Sunday given that it didn't rain before. So you have to take both into consideration. So to take both in consideration, this is what it is. Probability of it raining on Sunday is equivalent to, there's two scenarios. It either rains on Saturday and then rains on Sunday. So that's the first branch, that one. But then it could also be the second branch, which is not rain on a Saturday, then rain on a Sunday. So we have to add on an extra possible chance. Didn't rain on Saturday and it rained on Sunday, both of which is raining on Sunday. So putting them both together, we already got R and R, which we knew was 1/5. We haven't calculated not rain on Sunday, but then not rain on Saturday, but then rains on Sunday. So you have to calculate that. This is now equivalent to 3/4 or 0.75 times 1 out of 10. So that should be a plus there. Putting them together, that's now 1/5 plus 3 out of 40. To add fractions, you need to make sure the denominator is the same, so times 8, both top and bottom. That changes the fraction to 8 out of 40 plus 3 out of 40. So the chances must be 11 out of 40, which is not 80%. Okay, so that's the chances of it raining on Sunday. And that's practicing conditional probability overall to understand how does the second branch affect the first branch. The first branch affects the second branch. And as you're working them out, just knowing what the question is asking. So C is the one that's tricky. A and B is the common one that most of you will start practicing and get better at. It's that C part. Sometimes they'll put a spanner in the works. They might say, find chances of raining, union raining. And that's where you have to get a bit more creative. So if they use unioning or intersection, those are the times you have to think about tree diagrams, two-way tables, and Venn diagrams to help you solve. Okay? But I'm going to stop there. That's the example for conditional. This is what you will be required to do for 9F. Okay, now if you go through the Year 12 questions, you'll see that it gets a bit nice and trickier, but same essence as you practice that. Okay? That's 9F. 9G is independence, only one rule to prove. And that finishes off Unit 1. So the next lesson, you'll have time to work in your own space, and I'll come around and help you with probability, but all the solutions are there for you. Okay, if there's holiday homework, then I'll post it out to you or give it out to you on Friday. Otherwise, this is all you need to know for now. Okay?